All right, let's just jump right in. How would you go about building an API platform for an entire nation? I'm not talking about just a successful app. No, this is about foundational infrastructure, the kind that has to handle billions of transactions for hundreds of millions of people. Today, we're going to unpack the strategic framework behind India's massive Aadhaar project. And believe me, it's a blueprint for anyone who's ever been tasked with building something at true hyperscale. And look, when we say hyperscale, we really mean it. The system was designed from day one with this number just burned into its DNA, 1.2 billion potential users. This isn't just a storage problem, not by a long shot. We're talking about handling millions of enrollments and up to 100 million authentication API calls every single day. That's a scale that just completely throws the normal architecture rulebook out the window. So if you're an API product leader or an architect, this is the question for you. Right? The patterns and practices that get you to 1 million users, they're going to absolutely crumble under the weight of 1 billion. This is not about making incremental improvements. It's not a little tweak here and there. It demands a totally different mindset. So, what does it actually take to succeed at this level? All right, so here's how we're going to break this down. First, we'll just quickly frame up this whole hyperscale problem. Then we'll get into the real core philosophy, the guiding principles. After that, we're going to get tactical with the development playbook. And finally, we'll talk about how to build to evolve, which is all about making sure your platform is built to last. So let's get into those principles. And this is key. Before a single line of code was even written, a set of core principles was locked in. What's absolutely crucial to get here is that success at this kind of scale, it isn't about picking the hottest new technology. No, it's about committing to a philosophy, a mindset that guides every single architectural choice you make from then on. And here they are, the big 5. These principles are pretty much the bedrock of the entire system. We're talking about everything from being API first and component-based, all the way to designing for failure right from the get-go. Each one of these is like a pillar, holding up the whole structure and tackling a specific challenge of building at this massive scale. So let's dig into a few of these in a bit more detail. Okay, first up, API first and component-based. What does that really mean? It means you're not building some giant monolithic application. Instead, you're building a really minimalistic core platform that exposes all its functions through APIs. The best way to think about it is like building with Legos instead of trying to carve a giant statue. Each little brick is small and independent, and that means you can test it, upgrade it, or even completely rewrite one piece without taking the whole system down. Honestly, that kind of flexibility, it's a superpower. Now, this next principle, it's a core belief in hyperscale engineering, and it sounds so simple. Everything fails. And listen, this isn't about being pessimistic. It's about being a realist. At this kind of scale, it's just a statistical certainty that things will break. Servers will die, networks will get flaky, software will have bugs. It's gonna happen. So the huge shift in thinking is this. You have to stop trying to prevent every single failure and instead start designing your system to handle failure gracefully when it inevitably happens. So, okay, how do you actually handle failure? Well, one of the key technical concepts here is something called idempotency. I know, it's a bit of a fancy word, but it stands for a really simple and powerful idea. An idempotent API call is one you can send over and over again, but it'll only actually do its thing the very first time. So imagine a network error happens. You can just retry the request safely, and you don't have to worry about accidentally creating duplicate charges or multiple user records. It's just absolutely essential for building a resilient system. So what does this design for failure approach look like in practice? Well, it translates into a pretty practical checklist. You build in redundancy everywhere for your compute, for your data, everything. You use asynchronous processing so one slow part of the system doesn't cause this huge cascading failure downstream. You actually design your applications to try and self-heal and recover on their own. And you are just constantly, relentlessly hunting for and eliminating any single point of failure you can find. And then, of course, there's security. Look, when you're dealing with the identities of 1 billion people, security just can't be an afterthought. It can't be something you try to bolt on at the end. It has to be woven right into the very fabric of the system, part of its DNA from day one. We're talking about end-to-end encryption from the instant data is captured all the way through to when it's sitting on a disk. Plus, you've got digital signatures on all the API calls to make sure you have a guaranteed, unfakeable audit trail. Okay, so those are the big principles. The why. But principles are pretty useless if you don't have a process to turn them into reality. So let's shift gears and get into the playbook. This is where we see how that strategy gets turned into an actual, actionable development process. The whole development process kicks off with a super sharp, minimalistic vision. From there, you architect for specific kinds of workloads, you select your technology based on those principles we talked about, not just based on hype, and then you move into publishing, monitoring, and this cycle of continuous evolution. But I really want to focus on that second step for a second, architecting for different workloads. This is one of the most critical decisions you can make, separating your architecture based on workload type. Just look at the two core functions here. You've got enrollment on one side and authentication on the other. Enrollment, that's a one-time, heavy-duty process. It can happen in the background, take its time. But authentication, that needs to be a real-time, super lightweight, sub-second API call. It's like you just wouldn't use a cargo ship to compete in a speedboat race. They're built for different things. And these two workloads demand completely different architectures, different APIs, and yeah, different data stores. And that same thinking extends directly to your data strategy. You know, this idea of finding that one magical database to rule them all, it's a total myth, especially at this scale. The philosophy here is simple. Different data stores are built for different purposes, and a smart hyperscale architect always uses the right tool for the right job. And you can see that right here. For instance, for those core records that just have to have absolute reliability and consistency, think ACID compliance, the team used something proven, like MySQL. But for the crazy high volume and super low latency needed for biometric lookups, they went with a NoSQL store, like HBase. Each one of these choices is totally deliberate, and it's optimized for a very specific API workload. And that right tool for the job principle, it applies to the application layer too. The choice here was to go with lightweight, nimble frameworks like Java SE and Spring, and to actively avoid those big, bulky enterprise application servers. And this was paired with a really powerful orchestration pattern called stage-driven architecture, or SADA. The easiest way to think of it is like setting up a digital assembly line. You create these explicit cues and controls between each stage of a complex process. And what this does is help you manage the flow of requests across a huge distributed system, which is crucial for preventing a bottleneck in one little area from completely overwhelming everything else. All right, so you've built it. You followed the principles. You used the playbook. But guess what? The job is so far from over. In fact, launch day, that's just the beginning. The final and maybe the most important phase is making sure you've built a platform that's designed to evolve. And that all starts with having deep, real-time visibility into what's actually happening inside the system. I love this analogy. A hyperscale system needs a nervous system. Every single component has to be constantly sending out signals, emitting events about what it's doing. But just monitoring basic stuff like CPU and memory, that's not nearly enough. You need a business-centric view. You need to be able to answer questions like, how long are authentications taking in this specific region right now? Or, hey, is this one particular type of transaction failing more often than it should? All of that data, that telemetry, it feeds everything from your ops dashboards all the way to your real-time fraud detection engines. And really, that brings us to the ultimate takeaway here. The goal isn't to build some perfect static system that's frozen in time. That's just impossible. The real goal is to use all these principles and processes to build a resilient, component-based system that is explicitly, intentionally designed for continuous evolution. You have to be able to rewrite parts, add new features, and adapt to whatever the future throws at you, all without having to do a complete, painful overhaul. So, I want to leave you with this one crucial question to ask yourself. The question isn't if your APIs will fail, because they will. The question is, are your APIs built to fail? Have you actually designed them with resilience, with idempotency, with recovery, baked in right from day one? Because when you're playing at hyperscale, that's really the only question that matters.